I'm Zizhi from USS Lab, Zhejiang University. Today, I'm going to introduce you the PLA-LiDAR, physical laser attacks against LiDAR-based 3D object detection in autonomous vehicle. I'd like to start with a brief introduction of LiDAR, which is widely used in self-driving car and robots for perception. And the LiDAR-based perception serves as a foundation of planning and control for self-driving cars. LiDAR can provide a precise 3D point cloud of surrounding environment by laser ranging and laser beam steering. During laser ranging, one point can be acquired. LiDAR emits a laser pulse at each direction, which hits an object and reflects back as an echo. The distance of that point can be calculated based on the propagation time. During laser beam steering, LiDAR can change the laser firing direction and scan the surrounding environment to generate a point cloud. In LiDAR-based perception, the point cloud will be fed into object detection model, and the model will output the detection results, includes the location, size, and the category of objects. LiDAR-based perception is critical for self-driving. Existing works have proved that LiDAR points can be manipulated by laser, but they didn't consider the subsequent impacts of object detection. Some works focused on the 3D object detection and designed the adversarial attack to spoof detection model, but it is being mainly evaluated in the digital world. This leads to the question, is it possible to fool 3D object detection using lasers in the physical world? The answer is yes, with our PLA-LiDAR. By increasing the point number and achieving precise distance control of the point cloud being injected in physical world can successfully spoof detection model. There are two contributions of this work. First, we enhanced point manipulation capability. Second, we proved the feasibility of physical laser attacks against LiDAR-based 3D object detection. In PLA-LiDAR, we assume the attacker may set up the attack device in roadside and shooting lasers to the car with LiDAR on it. Well, two attack effects can be envisioned. For vehicle 1, so there are no obstacle ahead, an attacker could inject spoofing point cloud into the LiDAR, causing the detection system to mistakenly detect the pedestrian in front. The second is hiding. For vehicle 2, there is a pedestrian in front. The attacker may hide it, causing the model fails to perceive the real pedestrian. However, achieving physical laser attack is not trivial. First, we have to face the interference of surrounding objects. Second, LiDAR is scanning and rotating in very high speed, which increases the difficulty of point injection. Third, when controlling the distance of points, we will encounter a curse of light problem. Any small time error output by the speed of light will result in a large distance error. With the three difficulties, we have two challenges. First is how to make the attack signal be considered as a valid echo with the interference of surrounding environment. The second challenge is how to have a fine control of the inject point cloud with LiDAR's high-speed operation and the curse of light. To figure out how to make the attack signal be considered as a valid echo, we introduce return mode first. For a single laser ranging, multiple laser echoes are possible because of beam divergence and interference. Therefore, LiDAR adopts 3 different return modes to filter out valid echo. They are strongest, last, and dual. The default return mode is the strongest. This is based on the assumption the echoes with higher intensity come from environment that are more critical to be detected. Since the shape of an echo is just a pulse, it's easy to be forged. And then, as long as the power of a fake echo is high enough, it will always be considered as a valid echo. What's more, the real echo will be ignored. This allows us to easily hide specific points. With the insights above, we tested the laser with different wavelengths, peak power, and the pulse repetition frequency. We find different point cloud can be injected, including scatter, wave, broken wall, and a wall. Among them, War is the most stable one and has up to 4,000 points, which is 20 times more than prior SOTA work. And we found that the appropriate wavelength, high peak power, and precise repetition frequency are critical parameters to inject large number of points. To answer challenge 2, how to have a fine control of the injected point clouds, we designed the PLA-LiDAR, which includes 3 steps. Step 1, design the point cloud to either hide or create objects, which requires point cloud being injectable. Step 2, convert the point cloud into laser signals, and the signal should be able to fully preserve the shape and location of the point cloud. Step 3, inject the signals into the LiDAR to generate desired point cloud, which requires precise synchronization. For step 1, in order to make the point cloud injectable, the point cloud should follow the physical constraint as every generated point can only locate on one of the LiDAR's laser rays.
So, Zizhi, can you hear us?
Yeah, I can hear you.
Okay, so
did I just disconnected?
Okay, so can you go to the evaluation and continue from there?
Evaluation, okay.
Yeah, we trust that you have a very strong attack, so let's go to the evaluation.
Okay, thank you. I'm sorry for the network.
It's okay, never mind, just continue.
Oh, okay. We designed the PLA-LiDAR. According to different point design methods and attack effects, we can achieve 4 types of attacks. There are naive hiding that makes real point cloud of near objects to disappear completely. Recorder-based creating that can create a spoofing point that resembles a real person at a designated location. Optimization-based hiding that injects a small amount of points on top of a pedestrian, causing the pedestrian to be undetected. Optimization creating that injects the adversarial points and makes them to be detected as a pedestrian. All of them are realized in physical world. We have evaluated the 4 types of attacks on 2 LiDARs and 3 detection models. Our attack device includes a receiver, a delay controller, signal generator, and a laser transmitter. The overall attack success rate is shown in the table, and we have 2 observations. The first is VLP16 is more vulnerable to attacks than RS16 because RS16 LiDAR adds a certain amount of period randomization during its operation, which mitigates our attacks. The second is the performance of naive attack, including naive hiding and record creating, is better than optimization-based attack. This is because optimization attack has a higher requirement on timing. We have also evaluated the attack on a moving car. We integrate the attack equipment into a car, and the victim car is equipped with a VLP16 LiDAR on it. We improve the attack hardware to mitigate the jitters when vehicle is moving. We found it is feasible to realize attack on moving vehicle, so the success rate is slightly lower than the stationary setup. There are the 2 demos of moving attacks. Both cars are moving with a speed of around 5 kilometers per hour. For hiding attack, we can hide a target car in front of the victim LiDAR. And for creating attack, we can inject a spoofing point cloud that resembles a pedestrian. We encourage you to visit our website for more demos. To mitigate our attack, LiDAR pulse encoding and randomizing are promising defense mechanisms. Besides, sensor fusion is also a potentially effective approach. In summary, we propose the PLA-LiDAR attack that enhanced point manipulation capability, and extensive experiments are evaluated in physical world. The key is to raise awareness within the community about laser security by demonstrating the physical threat posed by laser. That's all of my talk. Thanks for listening. And sorry for the network again.
Okay, questions? I have a question for you. So when you tested moving vehicles, were the victim and attack vehicles moving at the same speed?
Yeah. They are at the same speed, about 5 kilometers per hour.
So they're relatively stationary, right? Because they're
Yeah,
moving
yeah,
at the
they are
same speed.
relatively stationary. But we have tackled the jitters. We have conquered the jitter problem when moving, but we didn't conquer the aiming problem yet.
Okay.
Because we think the aiming may be a mature but kind of complex engineering issue.
Cool. Any other questions? I have one more question. So when you injected the objects, did you consider them the object detection model, because you skipped through the details? So are you also attacking the model behind the sensor or just the sensor itself?
Yes, we directly spoof the detection model.
Okay.
By physical world.
Okay, cool. Well, thank you for this very cool work. Okay, let's thank the speaker again.